So our topic was soccer, and I'm Jeremy.
I'm Anna.
I'm Brianna. Oh, I'm gonna try to figure. Okay, so why we chose soccer is because all three of us are in soccer, or have been, or yeah. And we wanted to see how calculus intertwined with a game that we enjoy playing. And with choosing soccer, we were able to find the area of the dome, the area of the half circle, and then some punts that we were doing the area under the curve. Like that.
Okay, so the history of soccer. Soccer first developed in China in the 2nd and 3rd centuries, and it started off with kicking a leather ball into a net. And then at times the game started getting too violent, so it was banned in 1365. And then in the 1800s, soccer was welcomed back, and they had new rules that people had to follow. And if the rules weren't followed, it was considered rugby. And then in 1904, the Federal International Football Association, that are known as FIFA, was developed. And the first World Cup game took place in Uruguay. And yes, that was in 1904. And then the last World Cup game that was held was in 2014, and that was in Brazil. And then the next World Cup game that will be happening will be in 2018 in Russia. And soccer is today the most popular sport in the world, and more than 240 million people around the world play it. So it's pretty good.
Oh, there's our picture.
Alright, so I wanted to look up where the word soccer comes from because 4 countries call it soccer, and we're one of those. So as I was saying, in the 1800s, it was starting to become popular again, but there were many different games that were all played with your feet, so many were called football. So a group of teams in London in October 26, 1863, they gathered and formed a set of rules called association football. And then this, in British schools, then this kind of turned into a soccer, because they like to put R at the end of things, and then a soccer was easier than association football. And this caught on, especially in countries that had really popular games that already were called football. Like we have American football, and then Australia has football and rugby and stuff like that. So United States, Canada, and Australia, and then there's one other one in Africa that calls it soccer.
Alright, these are our measurements of the field that we use in our calculus. This is the center circle, the radius of it is 10 yards. The length of the field is 130 yards, and then the width is 100. And then this is the 18, which is 18 yards from the goal line, and then the 6. And then the PK, which is right here where if you have a penalty kick, it's 12 yards from the goal. So those are just some of the measurements that we used.
Okay, so our first math problem, we wanted to find the volume of a soccer dome. And we were going to do the volume of the soccer dome at SCSU, but the only measurements that we could find were of the actual field and not the distance between the field and the dome itself. So I found this one called the ASATI structure, and it's in New York. So first I just changed it into yards, since that's what a soccer field is measured in. And from there, I used the equation to find the volume of the dome. And then I had to figure out what A was, so I plugged in 0 for the X and Y. And from there, I figured out that A equaled -40 over 66.665 squared. And then from there, I put it back into vertex form, and then got that equation and figured out that it equaled 3,555.466. And so then from there, I had to take that and multiply it by the length right here. And after that, we figured out that the volume was 794,042.3707 yards.
Okay, so the history of integration was first documented technique of determining integration was called the method of exhaustion. It was created by Eudoxus in 370 BC, who was an ancient Greek astronomer. And then it was further developed in the 3rd century BC by Archimedes, and it was used to calculate the area of parabolas and areas of circles. In the 17th century, with the independent discovery of the fundamental theory of calculus, was created by Newton and Leibniz. And then the integrals are used in many different math problems, and it connects the distinction between integration and differentiation.
So here we just wanted to figure out some of the measurements if we did like calc on the field. So this is like the center circle where games are started off, and it has a radius of 10 yards. So we wanted to see if we did an over approximation and an under approximation of it, which one would be more accurate. So right here we did an over approximation, but we did it all the way around, and we got 343.705 yards. And then doing an under approximation, we figured out that it would be about 263.705 yards. And then just taking the area of a circle, doing pi r squared, we figured out that the actual area would be 314.159. So in the end, we figured out that for this particular problem, an over approximation was more accurate because the over approximation was only about 29 feet off, or yards off, and the other one was about 50 yards off.
That seems to be because if these were like perfect triangles between these points, then like they would be equal distance away because they'd be equal distance, or they'd be the same amount of area on one side, like the empty space, as on the inside of that approximation. So then it'd be exactly the same, but since the circle curves outward, it curves more towards the over approximation, so it fills up more of that area and becomes, or so the over approximation is more accurate than the under.
Okay, so then here's just kind of history of Riemann sum, how we did our over approximation and under approximation. Riemann sum was named after a German mathematician named Bernhard Riemann, and he was born in Germany in September of 1826. He was the second born out of 6 children. His father tutored them when he was young, and then they went to public school. And he was always really interested in math. So from 1826 to 1866, he became one of the leading mathematicians of the 19th century. And from there, he started looking into integration, and he viewed it as more of a simple process that was just basically a reverse to differentiation. And then he started approximating sums of the definite integrals. And from there, he was submitted to the faculty of Göttingen in 1854. And his submissions were not published until 13 years later, and then they became known as Riemann sums, how we know it today. Okay, so this one, we just kind of wanted to figure out for fun. So we took a video of me juggling and saw that after 6 seconds, I juggled the ball maybe 12 times. And if you guys don't know what juggling is, it's basically just keeping the ball in the air with either your knees or your feet or your head, basically anything but your hands. And then from there, I wanted to figure out the different time periods, how many juggles I could get. So if my rate stayed constant, after 1 minute, I would juggle about 120 times. And then with that same constant rate, after 1 second, that would be about 2 juggles, and after 1 hour, that would be 7,200 juggles, but I'm pretty sure that's impossible to keep that constant.
And then this is how tall the ball is based on time. And then with Anna's punt, we figured this out on the tracker thing that her equation would be negative 19.46 t squared plus 46.5 t minus 6.02. And then Jeremy's height would be negative 16.26 t squared plus 36.17 t plus 1.864. And then, so this one's Anna's punt, and then this one's Jeremy's, and just some cool gifts for them. And then for the maximum height, we figured out negative 38.92 t plus 46.5, which is 0, and then so t would be 1.194, and then the height would be 21.751 feet. And then the other one, which would be Jeremy's, is negative 32.52t plus 36.17 at 0. And then for time it would be 1.112, and the height would be 21.979 feet.
Alright, so derivatives as like a topic of trying to find the instantaneous rate of change has been going on for a while, but the first instance that I found of somebody being fairly successful at it was 1930s Pierre de Fermat, when he kind of did this thing as we do today, where he has f of x plus e minus f of x all over e. So we use delta x now, but he used e, and he would like make e smaller and smaller. The issue is that as he would do this, he would get to a point where e was 0, and he was dividing by 0 in his solutions, and you didn't really know why that worked, but the math still checked out anyways. And also he couldn't do this like universally. He could solve some polynomials and stuff, but it wasn't a universal method he could use everywhere. And his problems weren't solved until Newton and Leibniz came along, and they introduced this idea of limits, that as delta x, as e goes to 0, this becomes true, not when it is 0. And then they also expanded the usefulness of derivation, so we can use it on more than just a few equations. Alright, so here I wanted to know like how fast the ball slows down when it's like being passed on the ground versus how fast it slows down when it's being punted in the air. So I took, instead of trying to model where the ball is based on time, I just modeled its x distance away from its starting position based on time. And using that, on passing and then on punting, and using that I then took the derivative twice to find the acceleration. And the acceleration for punting is -4, and this is in feet per second. And then the acceleration for passing is -11.6. So with passing, it slows down almost 3 times as fast as when you punt it through the air because of the less resistance.
For the history of velocity, it's just the combination of speed of a moving object and the direction in which it's moving in. It's measured in like distance per time, so like yards, feet, or meters. It's also a rate of change. And Newton developed the 3 laws based on the ideas of derivatives and integrals, and that is how he dealt with calculus.
Alright. I'm sorry, Ethan, you're gonna be hurting watching this. So I wanted to know like how much of the goal I could cover with my 2 dives. So basically I just kind of fell to one side because I suck. And then I modeled the farther extension of my hand at each point. And then I did that, made an equation for that, and then found the area under that curve. So this is the equation for my left dive, our perspective, not from my perspective when I'm actually doing it. So that one. And this is for my right dive. And then this is integrating them to find that, so 58 feet and 49 feet, that's 107, which with a goal that is 8 by 24, so 192 feet, I'm covering just over half of that goal, which is pretty sad. Yeah. Let's just get rid of that.
Oh, well, okay. That's everything.
Good job.